Okay, so we're going to start off chapter 8. We're going to talk about different types of chemical bonding. There's going to be 3 big ones we talk about here. And this will cover the majority, pretty much everything. And this is all we're going to talk about in this chapter. And you've heard of the first 2 before. So ionic, that's, ions with ions. They're attracted by opposite charges, positive, negative, opposites attract. I've been trying to make that point over and over and over again if you had Chem 221 with me. And guess what? It carries forward in the 222. It doesn't go away. So negative things are attracted to positive things, just like the electrons are attracted to the nucleus, because the nucleus is a positive charge full of protons. Holds the atoms together, and it also starts holding together things made of multiple atoms. And so ions, you have a cation, you have an anion, they attract. You have covalent compounds. We've talked about these before as well. So these have shared electrons. These have chemical bonds. And so we're going to build some chemical instincts in this class as well. These rules that I'm going to talk about aren't always true, but they're a great kind of first anticipatory approach. Like you look at something, you can have some expectations. It might defy those expectations. We'll get into more details on stuff later. But generally, if something's ionic, you're going to see a metal and a non-metal, or you see a polyatomic ion. That's another giveaway. Something like phosphate or nitrate, stuff like that. Now they can show up in covalent compounds, but your first anticipation is, oh, this is probably an ionic thing. And there are some metals that can form covalent bonds in the right situations, but generally, metal and non-metal is going to get you ionic. So if you see a metal making bonds, you go, that's unusual. And we'll talk about it. But again, like more often than not, this is the case. Covalent, sharing electrons, typically they're going to be all nonmetals. They're going to have equal electronegativities, or not equal, but close enough that they can't just take the electrons and run. They can't just be like, give me that electron, sodium, and it runs off with it. Sodium's left 1 electron less as a cation, and maybe chlorine did that. It becomes chloride, Cl minus. You get table salt, sodium chloride, as a result of that. But typically, all nonmetals, covalent compound. And then metallic, well, this is an aluminum marker I'm using. This board has an aluminum tray. That is all metal atoms, all aluminum metals. And so metal compounds are able to be held together through metallic bonding. And we're going to get into some details on these in a little bit, but that's the first situation. And so this is just, something's all metal atoms, it's metallic bond. And then you've probably heard the term alloy before, and that's just a mix of different metals. So there's titanium metal, but it wasn't very useful. It was somewhat brittle, if I remember right. I'm going on the internet, I should probably fact check stuff, but whatever. But titanium alloy was the game changer. They started mixing in other metals with it and getting better properties. So they got the strength of titanium, the weight reduction of titanium. It weighs less than something like iron. It's further up the periodic table, so the atoms weigh less. But by mixing with other metals, they're able to get better properties out of it. So alloys are very important. In fact, there's a number of alloys that you probably see every day. Stainless steel is an alloy. Steel itself is an alloy. And there's a ton of different mixtures. They move carbon atoms in there, nitrogen, stuff like that. So it doesn't always have to be just metals being mixed together, but it's metals that have a mixture in them. So it's not a pure elemental compound. All right. So ionic compounds, shouldn't be too game changing, but we make sure we get our facts straight here. So right off the bat, no shared electrons, right? Smash and grab. Anions have taken electrons from cations. They're stuck together. Why? Because they're oppositely charged. They're not sharing. Cations are emptying their valence shell. Anions are filling their valence shell. And, these are filling p orbitals and s orbitals, all that stuff. We're not too concerned about that. Or emptying them, or d orbitals, or half emptying d orbitals. Oh joy, right? So, no shared electrons, which means our opposite charges stick together. They get stuck on each other. All right. And then, there's an equation for this. So the potential of the attraction, so the force that holds these together, is proportional. That's what the alpha means here, proportional. Not totally equal, there's some variables we're leaving out. But it's proportional to the charges divided by the distance between them. So these are our charges of our ions. Q1, Q2, gotta have at least 2 ions to play the game, right? And then D is the distance between the ions. So, what we have is a situation where ionic attraction is going to increase as the charges of the ions increase. It's also going to increase as the distance between them becomes smaller. So what does that mean? What does it mean for the distance between them to be smaller? Well, it means the ions are getting smaller. So something like, if you look at your periodic table, potassium is going to be a +1 cation. But it's in the 4th row, it's going to be very large. If we compare that to, say, lithium, which is in the 2nd row, and its ion, it will be much smaller. It'll have 2 less n values of orbitals around it, so it will be much smaller. And so that means that lithium is going to have a stronger ionic attraction than potassium because the nuclei, when we say distance between the ions, we mean from the nuclei, from the center point. Those center points squeeze together. The larger the sphere is, the farther those nuclei get apart. So larger ions, less attraction. Lower charges on ions, less attraction. So conversely, we can flip it on its head. Sometimes it's easier to think, bigger is better, right? So larger charges. So like magnesium 2+, that's a 2 charge. That's larger than a sodium +1. That's a larger charge. It's going to have a larger ionic attraction or a larger contribution to it. And then smaller ions will also have larger ionic attractions. So you're looking for 2 features for what's going to be like, held together most strongly in an ionic compound. The charges involved and the sizes of the ions. And apply those trends I talked to you about earlier, and you can figure out what's held together more strongly. All right? So, the next one, covalent. So these have shared electrons. All right, so now we're really talking about bonding. For me, sharing electrons means bonding. I don't like the term ionic bonding. Your book uses it. Everyone uses it. I think it's a terrible term. Metallic bonding is, it works. The electrons are being shared too. We'll talk about it. But covalent, we talk about this. This is shared electrons. And those shared electrons kind of rubber band the molecule together, or 2 atoms. So it's always between 2 atoms. So they're rubber banded together. So these are dynamic, like ionic compounds. They you ever seen a McDonald's ball pit? You've seen a model of an ionic compound. They just sort of stack together. And a covalent compound is rubber banded together. So there's 2 atoms. They're not ions. They're not stuck together. They're rubber banded together. So they can move apart. They can come together. We call that vibrational motion. So that can happen. So if they get too far apart, the bond brings them back together. If they get too close, their nuclei repel each other and they move back. And so the potential on these is a little bit trickier. We're going to show that in a second. Now these chemical bonds store energy. And that's going to be a big topic later on. We're going to have a whole section on that. But bonds store energy. We rearrange chemical bonds. We talked about this in chapter 5. You do a reaction, you're rearranging chemical bonds. There's energy involved with it. That's what we talked about in chapter 5. Delta H is coming back later. I know everyone just had horrible flashbacks. So we're not done with it. It's coming back. But we'll have a different perspective on it, centered on the idea of chemical bonds and them storing energy. So therefore, if we go from bonds that have a lot of energy stored in them to bonds with less energy, they release that energy and it's an exothermic process. Energy or heat has exited the reaction into its surroundings. So, but we'll talk about that. All right. And this is typically all nonmetals. Every now and again, a metal can get in there. There'll be some exceptions. But, you know, again, building those chemical instincts. You see something that's all nonmetals, you're like, covalent. Okay, no big deal. You see a metal mixed in there with it, you're like, it's probably ionic. Maybe you do your legwork, make sure it's not covalent, but typically that's kind of the breaking point. And I'm not gonna get super cute with you guys on this. Like I said, I like to build these chemical instincts. So you can be surprised later when they get broken. Like chemists love to be like, oh, this is the way things are, and then, oh yeah, over here is some other detail. For example, we're like, oh yeah, valence shells, blah, 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 electrons go in these shells, increasing size. And chapter 7 comes along and goes, oh, actually, there's a little more to that. They have these special shapes, we have these quantum numbers, they used to have addresses, you know, can't have two electrons with the same set of quantum numbers, Pauli exclusion principle, yada, yada, yada. They're spin up, spin down. So building a base, and then going up from there, you know, got to build a foundation. And so that's what I'm really looking to do in this chapter is get you some instincts. How do you know something's ionic or covalent? Look at what it's made out of. All right, and so if this is our electric potential for an ionic compound, nice little proportional formula, I'm going to draw a graph. I'm going to draw a picture for covalent. So we've got our electric potential, the attraction between the two atoms, and this is zero. So zero potential means zero attraction. We're going to run that out. And it does something like this. And at this lowest point here, there's always a bowl right here. Right at the bottom of that, that's your average bond length, because our x-axis is our internuclear distance. So, as the nuclei get farther apart, they want to be here, the bond brings them back together, they go to the lowest energy point. Now, if they get too close, well, guess what happens? Two things can't occupy the same space. So we have this situation. We've got our two atoms. They move apart. The bond is like a rubber band. It pulls them back together. If we were to get them infinitely far apart, they have zero attraction. They don't see each other at all. But as they get closer and closer, they start noticing each other more. They make a bond. They stay in average distance. Now, if they get too close, two things cannot occupy the same space. I can put more and more energy into these atoms. They are not going to occupy the same space. Now there's a whole chapter where we talk about nuclear fusion and stuff. So it's a whole other process, but no chemical process is going to do that. They're not going to fuse together and make a new nuclei. And so this essentially goes up to infinity. Because we'll never actually be able to make them occupy the same space. They just rearrange to be a little closer together. That's the best we can do. And oh man, you figure that out, you just solve the world's future energy crisis. At least, well, if you can do it in a way where you get more energy out than you put in, that's been the secret. Knowing how to do fusion for quite a while now. And if you ever wonder, like, is that really a thing? Just look at the sun. It does it every day and every night. We just don't see it happening. So, look up there. All right. So the last one, metallic, all right? So all metals. So these kind of share electrons. The way this is often described is a delocalized, we'll break this down, but this is a delocalized sea of electrons, all right? So what does that mean? Well, metals typically form cations. They typically dump electrons the second they have the opportunity to form an ionic compound. And so what happens is these metals don't want these electrons. That's what's going on. They do not want the electrons. They're pushing them off on the anions. Anions are happy to take them on. Well, what happens if there's nothing around to be an anion? The metal's still trying to push the electrons off. You know, this is like you've got a 3-bedroom house and 5 kids. You're trying to like, go stay with your aunts, go stay at your friend's house, go wherever. Like, yeah, get out of here. Like, I want to be able to, I don't know, do some paper mache or something, whatever it is people do with their time. You know, watch some Netflix in peace, whatever it might be. And so you're pushing them out, they're pushing them out. These are what the metals are doing. They've got electrons they don't want. They're just trying to push them out. Now, if the only thing around is other atoms that don't want electrons, guess what you're pushing them onto? It's like, oh, I have the 3-bedroom house and the 5 kids, and now my neighbor's kid is staying over for the night. Oh, great, that's wonderful. Well, I'm just gonna try to push them all off on my other neighbor. And that's what's happening. And so that is what allows metals to conduct electricity. And the fact that they are actually sharing electrons through this process means they hold together very nicely as solids. And all the features of metals that we know are because of this metallic bonding. So they can carry electrons through them. They can conduct electricity. Not all metals are good at it, but some are very good, some less so. Because you can essentially pull an electron off one end and replace it on the other, and they all just shuffle down the line. They're all just like, oh, cool, and push electrons, bye. Like, you know, you're sending all the kids down. All right, so it's this delocalized sea of electrons. That's the idea. That's what's holding it together. So the details, we've talked about this, but let's get it in writing. So first off, our metal atoms are trying to push unwanted electrons on each other. That's what's going on. So metal atoms pushing unwanted electrons onto each other. They're all trying to just, you know, only have their 3 bedrooms full, no more people sleeping on the couch or whatever. That's what they're trying to do. That means that these electrons, you know, if I'm an electron in a metallic compound, I'm not associated necessarily with any particular, at least if I'm a valence electron, I should say. If I'm a valence electron in a metallic compound, I'm not associated with any particular atom. So I'm in a room full of chairs here. We'll say those are the nuclei. If I'm an electron, I can move freely around between all of the chairs because I am not really wanted by any of them. All right, that's what happens. It's one of those facts. I feel like everyone's had an experience in their life where they can relate to being like an electron in a metallic compound. I know I certainly have probably more than my fair share of those, but whatever. And so you move around, and that means that you're highly mobile. So these electrons are highly mobile. And that, whoops, always tough to write on the bottom of the board, even when I'm on camera. Give you the full classroom experience because of my crappy writing on the bottom of the board. You're welcome, everybody. So electrons are highly mobile. Well, that means that they can conduct heat and electricity very effectively. So that means that they conduct heat and electricity. So that's why metals are able to do that. It's the unwanted electrons being pushed around for electricity. That's why we have metal wires. It's the unwanted electrons that pick up heat energy and move around with that. Vibrational motion. Carry that around effectively. So metallic compounds have a different type of bonding. They're not ionic, they're not covalent. They're somewhere in between. They're like half ionic, half covalent. They're sharing electrons, but not because they want electrons, because they want to get rid of electrons. Covalent compound, generally everything wants electrons. That's why they're sharing, because if one side doesn't want the electron, you've got ionic. You got something that wants electrons and something that doesn't. And they team up and they go, thank you. You know, the metals are adopting out their unwanted electrons permanently, and they're happy to do it. And they're a metallic compound, they can't find any takers. That's what's going on. Got these different potentials for ionic and covalent. Don't worry about metallic. It's not really the same sort of detail. But yeah, this is what breaks down 3 types of bonding. Bonding is the central theme of this chapter. So we're going to go into more detail, especially on covalent, a little bit on metallic, but more in the solids chapter. So that'll be later on. And ionic, that'll be in the solids chapter as well. There's really not a lot of magic there. It really is, if you've seen a McDonald's ball pit, you've seen what these compounds do. They're all spheres and they stack. All right. So that's it for this first part. We'll carry you through and keep going on some more of the chapter today.